Dear students, in this section of inorganic chemistry, we will learn about the basics of energy profile diagram. After learning and grasping this module, you will be able to understand about the diagrammatic representation of a chemical reaction. You can also know about framing of energy profile diagram and diagrammatic representation of different states involved in a chemical reaction. Now let's introduce the topic. Energy profile diagram is one of the most powerful tool to represent proceeding of a chemical reaction. Proceeding of a chemical reaction can be observed in terms of variation in any observable change like change in bond length, change in bond angle, etc. All these changes can be represented in the form of coordinates of individual atoms called reaction coordinates. And if we make a graph between energy against reaction coordinates, then the graph is called energy profile diagram. A complete diagram may make scientists enable to represent almost all parameters including thermodynamic as well as kinetic parameters of a chemical reaction. Now let's illustrate the topic. As we know, energy profile diagram is a diagrammatic representation of proceeding of a chemical reaction. Therefore, it can give entire information about a reaction. It will be better if we understand these type of diagrams in the form of examples. As we know, chemical reaction is a result of bond breaking and bond making process. And to break a bond, we need energy. The energy can be given either by thermal or photochemical process. Let's imagine a displacement reaction in which ligand Y- attacks over a metal complex Mx to form My. Energy is needed for breaking Mx bond and for Y- to overcome the repulsive forces, that is repulsion between electron density of Mx and Y-. So, because of supply of energy, Y- collides with Mx, and if collision met with proper orientation, that is, if Y- attacks on Mx from the side of metal, that is M, then Y- comes closer to M. At the same time, bond between M and X weakens up. So, from one end, Y- is coming closer, while at the other end, X- is moving away. A stage reaches where M has equal chances to form bond with X- and with Y-. Means bond distance between Xm and My are equal. This stage is called transition stage. If reaction crosses this stage, X- get away and product Ym forms with release of energy. Now let's see the entire reaction in the form of energy profile diagram. This single step reaction has three extremes. The collective energy of reactants at room temperature or at initial reaction temperature are shown in extreme left of the diagram. With supply of energy, reactants collide with higher energy, and due to which vibrational amplitude of reactant Mx increases. because of weakening of mx bond, Y minus get chance to attack on M from opposite end of X minus. So, YMX transition state forms, which is the maxima of the diagram, means energy is increasing from reactant to a transition state, which is the maxima of the diagram, and therefore highest energy and lowest stability of the stage is there. From the top of this hill, ball can drop in either side. If it drops in the forward direction, then a reaction completes and product My used to form. In a displacement reaction, we can have another mechanism, that is other path of a reaction. In this mechanism, due to increase of energy, holding two species, that is M plus and X minus in Mx becomes difficult. This kind of case generally we get where M has higher steric hindrance, and therefore bond between M and X becomes weaker. So, when we supply the energy, Mx breaks to form intermediate M plus and leaving group X minus, and in this process they both get steric relaxation. So, before reaching to intermediate, molecule get a stage where M and X is in equilibrium of the two stages, where Mx is neither bonded nor non-bonded. This stage is called transition state first. By the first step of the reaction, we get intermediate M plus and the leaving group X minus. In the second step, Y minus attacks on M plus to form transition state second, which represent a stage of equilibrium between both bonded and non-bonded form of Ym. After crossing this stage, product Ym forms. Energy of reactants from where reaction starts is plotted in the extreme left. Now, because of increase of energy of reactant Mx, vibrational amplitude of Mx increases and a stage reaches where it becomes difficult to hold both M and X together. Energy maxima where both Mx are together at highest possible vibrational amplitude is called transition state first. When reaction crosses this stage, energy decreases till formation of M plus, that is intermediate of the reaction. Now, M plus has vacancy, and in the second step there are chances for ligand Y to attack on it, and therefore in the second step, when Y minus come closer and attacks on M plus, a new bond may form. But before reaching to this stage, they both need to overcome from the repulsion created by the electron density on both species. Since M plus was unstable or comparably less stable with the reactant, so this requirement of energy can be fulfilled by the energy released in step 1. By this way, both the species come closer and reaches to a stage where both attractive and repulsive forces between M and Y are equal. The state of this stage is called transition state second. After this stage, attractive forces overcomes the repulsive forces, and therefore energy of the reaction decreases to form My. Please note that both the reactions are different even if symbols of the species are using similar in both the cases. So we had shown two different mechanisms, two different paths of nucleophilic substitution reaction in above two examples. Since path of two reactions are entirely different, therefore their energy profile diagram also differ. Here we are showing two mechanisms together in the form of energy profile diagram. In first figure you can see three extremes. First was for reactant, which was the energy of the reacting species collectively at the reaction temperature, that is initial reaction temperature. Now in the second extreme you can have a transition state which is of highest possible energy and for lowest stability. Now in the third stage you can get the product. While in second figure you can see a two-step process that involves two transition states, that is two peak of hills. These two peaks represent two different transition state, and in between the two transition state you can have one intermediate. These processes can be understood in the following point heads. So involved terminologies in the energy profile diagrams are the extreme minima of energy profile diagram that includes initial and reaction completion state are the representative of reactants and products. In general, these are the two most stable state of a chemical reaction. In an energy profile diagram of a chemical reaction, we can have several energy maxima called transition state of a reaction. Each step of a chemical reaction compulsorily involves a transition state. For example, in first figure of the reaction that we have shown include a single transition state, because in that reaction we had only one step process. While in second figure the diagram involves two step process, and therefore we have two different maxima, that is two transition states, which are represented as TS1, that is transition state 1, and transition state 2. Transition state of a chemical reaction is an extremely unstable state, and therefore in general do not exist for more than a picosecond. Now we are coming towards the minima of the diagram. Energy minima of the diagram other than that of reactant and product represent intermediate of the reaction. In between every two consecutive steps of a chemical reaction, an intermediate exists. It means intermediate can be treated as product of one step and reactant of other step, that it follows. Therefore, in a chemical reaction, total number of intermediate is one less than that the number of steps that it involves. The state is comparatively less stable than that of reactant and product of the chemical reaction, but is more stable that of involved transition state, and therefore its lifetime is in between nanosecond to microsecond. You can get here transition state is less stable than intermediate because it has higher energy. Its lifetime is in picoseconds, while intermediate is comparatively more stable and of less energy. Since this state can exist for comparatively longer duration, an intermediate can be tracked. Now let's learn about the energetics of a chemical reaction. A chemical reaction is a result of breaking of old bonds and framing of new bonds. Breaking of old bonds always need energy. Therefore, for proceeding of every reaction, it must have to cross an energy barrier. Energy of this barrier is called threshold energy for the reaction. A chemical reaction cannot be completed without crossing this barrier. Therefore, for proceeding of a chemical reaction, one must have to supply energy to the reactant at least to cross this barrier. The difference of threshold energy and that of the energy of reactant is called activation energy. From the law of microscopic reversibility, the path for the forward reaction and that of the backward reaction will always be the same. Therefore, theoretically, all reactions are reversible in nature. A chemical reaction is a result of breaking of old bonds and framing of new bonds. Breaking of old bonds always need energy, and therefore proceeding of every reaction requires energy to cross the energy barrier. The energy of this barrier is called threshold energy of the reaction. A chemical reaction cannot be completed without crossing this barrier. Therefore, for proceeding of a chemical reaction, one must have to supply energy to the reactant at least to cross this energy barrier. The difference of energy between threshold energy and that of energy of reactant is called activation energy, which was represented by EA in your previous figures. From the law of microscopic reversibility, the path for the forward reaction and that of backward reaction will always be the same. Therefore, theoretically, all reactions are reversible in nature. Chances of backward reaction is always available in a chemical reaction. The difference for an irreversible reaction is in activation energy of the backward reaction and in the feasibility of a reaction, that is in the del G values. Activation energy for backward reaction is represented by EA in the energy profile diagram represented in figure 1A and figure 1B. Energy profile diagram of a reaction can be plotted between reaction coordinates and in the enthalpy of reaction, or between reaction coordinates and free energy of the reaction, and similarly we can have several other possibilities. The difference of enthalpy of product and that of the enthalpy of reactant is called enthalpy of reaction or enthalpy of formation. A higher enthalpy of product compared to reactant indicate an endothermic process, that is, in order to complete such reaction we have to provide overall energy. Means the energy supplied will always be higher than that of the energy released by the system. While negative value of enthalpy change denote an exothermic process, that is, when enthalpy of product is lower than that of the enthalpy of reactant, then the difference between the enthalpy of product and enthalpy of reactant will be negative. Such reaction denotes an exothermic reaction. In a similar way, reaction coordinates of a chemical reaction can be plotted against free energy of a reaction. A higher value of free energy of the product compared to reactant represent a non-feasible or non-spontaneous process, and vice versa. Now let's summarize. Energy profile diagram is a powerful tool to see proceeding of a chemical reaction against energy of the system. It collectively represents energy or stability of reactant, product, transition states and intermediates. When energy profile diagram is shown along with the chemical equation, the two together can represent almost all thermodynamic, that is enthalpy of reaction, spontaneity of the reaction, etc., and all kinetic parameters, that is rate of reaction, reversibility, equilibrium, etc. for the reaction. Diagram can also be used to deduce important conclusions about a reaction, and therefore it is extremely useful in framing mechanism of a reaction.